We start this morning's session. My name is Richard Gibbons, and I'd like to invite Sean Meyn to give the first of our tutorial talks. Two tutorial talks yesterday, two more this morning from Sean and also from Glenn Binnican. And so, a particular pleasure to invite Sean to speak because Sean, I think probably above all others, have been the most supportive and enthusiastic encourager of the organisers to develop this meeting. I think in large part without his support and bolstering our efforts, it would have been a one-day meeting that we started off with, but somehow it's rolled into this 4-day extravaganza tutorial talk. So, Sean, if you'd like to.
Thank you very much, Richard, and thanks Stan and the other organisers. It really is an honour to be here and a very exciting time. I've enjoyed the talks by Ben and Danny very much, and looking forward to more engagement. So what I want to talk about today is understanding dynamic models and dynamic for dynamic markets, and basically I'm lucky because Ben gave a very nice overview of some of the key issues. I'll probably repeat some of those in the beginning of this talk. And if you did go to his talk, you might remember he mentioned the different ways of modeling for different purposes. So you may have simple models for the purposes of getting qualitative insight, and more detailed models for operations or other things, for more detailed forecasting. And I should add one more thing. So, for the purposes of control design, we often take simple models. And the reason is that we're going to design a control solution which is so robust that it's going to be able to withstand all the modeling error that's inevitable anyway. So that's my point of view. I'm sort of looking at control models for these complex networks to get insight and also for the purposes of policy design. And I'll explain more as we go along about how I can maybe justify these simple models. So this is joint work with Professor In-Koo Cho, an economist at Illinois, and my graduate students, Matthias is here, and Gui Wong and Anu and Asan at Illinois. So this is a bit much for an hour and 15 minutes, but again, I'll be able to skip through some of it fairly quickly because of we've already seen some of the issues yesterday. And what I would like to do is talk about, first of all, basically go through some of the issues that I see as important over the next 10 years. First, talk about the centralized control problem. How would I, if I was just could control everything, how would I schedule power and sufficient reserves to be able to make trade-offs between cost and reliability? And then the question is, can I try to achieve this beautiful, efficient utopia equilibrium through a market? And yes, we can, but the outcome is different than what you might expect when you actually take into account dynamics. And so this is work that In-Koo Cho and I did about 8 years ago on explaining the highly volatile prices you see all over the world. And the reason is volatility. And so when we look at what's going to happen in the future, especially in the United States with all these mandates for wind integration, it's going to mean more volatility and possibly more crazy prices. So that's what the main message in this talk. And so then there are lots of research. This is absolutely. I mean, there's a PhD thesis for every one of us. many open topics. So I'll go through a few of those at the end. Okay, so first of all, issues and approaches. And I should mention this a few times. Ben had mentioned negative prices in his lecture yesterday. This is just a beautiful example from Australia, where price went from $50 a megawatt hour to $10,000 a megawatt hour in Victoria. And in Tasmania, at the same time, it went to negative $1,000. I'll explain why in a moment. So first of all, a big issue is mandates. So it was really nice. There was a lot of emphasis yesterday on long-term planning. And long-term planning is incredibly difficult when you have no idea what the mandates will be tomorrow. Right now, for example, in New York, they're saying you have to have 29% renewable energy by 2015. Now, we could all plan for that and try to make money out of it as a business person, but by 2012, those mandates might go away. So it's very difficult. It's a huge issue. Of course, there's the dynamics of power. You can have instabilities. It's not just water flowing through pipes. There are mass spring models for power, and power sloshes around and has resonances, and you can have instabilities. It's a complex system. There's no way you can get a resolution high enough to show the intricate transmission grid in Europe. And so it's a complex interconnected system, again, with dynamics and with breakdowns and with potential of people wanting to manipulate the system, as has happened in the past. There's market power. So to learn about that, you can see what I'm told is a wonderful musical in Soho, playing until August. I'm going to see this on Friday. So when anyone talks about electric power and problems, immediately people in the US mention Enron and talk about these horrible people who did things like did repairs on their generators in the middle of the day in order to drive up prices. But I mean, we have to ask, are they really so horrible? I know they did some horrible things, but if it's their job to try to maximize their profits, and turning down a generator in the middle of the day is a way to do that, you know, if we think that's bad, then we should put the rules in place in advance. We should have a market design in advance which prevents people from doing these sorts of games. You know, why didn't we predict that Enron would make the prices go up? You know, why not? Right? So market power is a huge issue, and how do you control it? We're never going to have an infinite number of players. There's always going to be these issues. But I think, but equally important is there's so many risks to the suppliers. I mentioned mandates before. It's a big risk to generators because they have no idea what the rules will be tomorrow. And with the integration of wind, there'll be huge risks. Suppose, for example, that Cambridge decided to buy their own windmills. And so they wanted to take care of maybe 20% of their wind energy by just owning their own windmills. What would that mean? Well, it would mean that, you know, great savings overall in electric power because they get free wind energy. But what kind of business would there be then for the traditional power suppliers? You know, this is an example from the northwest of the U.S. where sometimes the wind gives you 2 gigawatts of electricity, which is something like a third of the needed power, and other times it gives you 0. So there's these generators sitting around that sometimes are asked to supply 2 gigawatts of power, and sometimes nothing. It sounds like a terrible business model unless they can charge a lot of money. And of course, there's what I would say is friction. So some people say, I must be market power. If you're suddenly charging me $10,000 per megawatt hour for power, and it was $50 a minute ago, it must be market power. And my answer is no, that's not true. This is an example of an efficient equilibrium of the form looked at by Milton Friedman and Gary Becker. The Chicago School's ideal equilibrium looks just like this, as I'll explain. And it's in economics, it's what's called friction. It's some lack of liquidity in being able to respond to demand. And that happens every minute in a power system because there are ramp constraints on generation, there are hard constraints on transmission lines. And hard constraints means Lagrange multipliers, sensitivity, and that means high prices. And it has nothing to do with market power. So here the problem was that there was a big demand for electricity in Tasmania, and as Ben and Danny explained yesterday, power, you can't tell the power where to go. There's Kirchhoff's voltage laws. And so as the power was being delivered to Victoria, it was also going through to Tasmania. And I believe the generators there had to provide a counterflow in order to avoid a transmission constraint here. And that's why in Tasmania they were willing to pay $1,000 a megawatt hour to deliver power. I've never seen the complete answer. I've never been able to get that, but that's my conjecture. And so, you know, there's all sorts of constraints, and that's a big issue in these problems. And again, the market and the physical system are tightly coupled, as this example shows. And I can show you, I collect these. I've got dozens of examples if you'd like to see more. So, of course, there's uncertainty, and that goes without saying. And, you know, if you look at the California ISO website any day, the Independent Service Operator website, you'll say that they keep about 10% or so of extra capacity on hand all the time, even though the forecast for power of the day is actually very good. The uncertainty in demand is not that large, and yet they still keep a massive amount of extra capacity, mainly concerned over breakdown. That's the concern today. Okay, so So how do we address some of these issues? So basically in this talk I want to get qualitative insight, but I want to be able to understand the impact of dynamics and constraints. And the first constraint is ramp constraints. The first simplest example I'll look at is where there are no transmission constraints at all. I aggregate supply of power, and I just have an overall ramp constraint. And that constraint comes from the physical technology. You can only ramp up power so much. But also the grid. If you kick the grid too hard, it will oscillate. And so you just can't move things that fast. So there's a lot of reasons for a ramp constraint. Next, I'll look at multiple levels of service. So I might have some generators with one ramp constraint and some with another. These could be, say, nuclear, where this is basically 0, and coal, where it's a bit better. Faster ramping generation is, for example, gas turbine sources. Gas turbine is a more responsive source of generation. And finally, I'd like to look at a whole network, and then I have these linear approximations for the power flow in the transmission lines, given the power injected into the system and the power extracted from the various nodes. This was reviewed yesterday. And I won't have much time to get into that, but anyway, we're going to go through this step by step. So in addition to these constraints, I'll put some statistical assumptions on demand as well. Okay, so that's in terms of modeling for the purposes of understanding reserves and control, scheduling different generators and all of that. What about the market? Well, in this lecture, I'm going to look at the most ideal circumstances, absolute utopia. So first of all, I'll assume that there is no Enron, that there's nobody who could possibly manipulate prices. And secondly, I ignore all externalities. So, there's no mandates, there's nothing at all. People can do what they want. But the main thing, they do what they want with the price, except they cannot manipulate the price. So this is the formulation from the Chicago School, how you get an efficient equilibrium. And also, when I look at the case of wind integration, I'm going to assume that we own the wind. The consumers, utilities own the wind, and so they don't even have to pay for it. It's free. And even under those conditions, we're going to see some crazy behavior in a unique, efficient market equilibrium. Okay, so first of all, sort of first part of the talk, reliability by design. How would California ISO come up with that amount of reserves, the amount of capacity against, based on the amount of demand? How would they come up with this 10% based on ramping constraints, volatility, all of that? Okay, and it's not. I mean, if you know if you're from the stochastic, the sort of the queuing theory, stochastic networks, the crowd, you know the answer to this already. I don't even have to tell you. Okay. For those of you who aren't, I'll give you the story. Okay. So I want to look at California ISO's first mandate, which is to operate the grid efficiently and reliably, assuming they control everything. And later I'll go to these other issues. In particular, how do you facilitate an effective market? Okay, so to do this, I'm going to come up with a diffusion model. It doesn't have to be a diffusion model. I'm only doing this for the purposes of computation. I can get closed form expressions for everything if I assume a diffusion model. If you don't assume, say, have all the assumptions I'm imposing, then you have to compute things numerically instead of analytically. The key variable here will be reserve, which is the available power minus the demand. So right there, that's the reserve, the distance between the available power and the demand. So the demand here, I'm going to look at the deviation. So I'm going to be looking at the real-time operation. There's an actual demand and there's a forecast demand, as we saw before. And G of t will be the deviation capacity for the day-ahead market. So, 24 hours ago, there was a schedule of power assigned, and maybe we'll need a little bit more, maybe a little bit less. And I'm defining G of t to be that deviation. Yeah, that's right. So it's in the case of California, it's very, very small. But if you look at smaller markets, it's much more volatile. Has a larger variance, and And California is a bad example in a way, because can you really get power from the very north to the very south instantly? There are losses and all sorts of issues. So really I'm thinking of a smaller market than all of California, where there'd be more volatility. Yeah, it turns, yeah, subtracting the deviations is the same as subtracting the full, everything cancels. Yeah. Okay, so again, for the purposes of computation, I'll assume that demand, this deviation demand, is a driftless Brownian motion with instantaneous variance sigma squared. In smaller markets, that doesn't look too bad. It's a reasonable assumption, especially on a shorter time window. And again, I have this assumption of friction, that the generation can't increase instantaneously. I've got this ramp constraint. And I'm only imposing an upper ramp constraint here. Again, I could impose lower ramp constraints as well. The problem would get much more complex.
But there would be periodicity, right? The demand.
Yeah, in real life, the actual demand is periodic. I'm just looking at the deviation over a period of time of 6 hours or so.
Predictable.
Yeah, yeah.
So it is subtracted periodic part away.
That's right. I'm subtracting the periodic part from and looking at maybe a 24-hour time period or a 12-hour time period. Okay, so here's what's called the social planner's problem in economics. Basically, I've got three welfare functions here, and I've got a discount rate gamma, and I want to minimize this expected discounted welfare over all possible policies. And by policies, I mean, do I ramp up generation or do I ramp it down? Okay? That's right now. That's all I'm talking about is one decision. Do I ramp up, and how fast, or do I ramp down? So I've got a supplier's welfare, which is the amount of money they're bringing in minus their costs. I've got a consumer welfare, which is the utility of consumption minus the payments they have to make to the supplier, and minus the cost of blackout. If I don't have enough power, the power that I need, it means I have to shut down some of the part of the city, and in some cities that means a lot of money. So that cost of blackout can be, $100,000 a megawatt hour.
Is that different from no utility?
Yeah.
That's the actual cost?
Right. So. I'd say they're subtly different, but I think it would take some time to discuss that, yes, but they're virtually the same. And I can't resist putting this in as well. So there are all sorts of other welfare issues to consider. There's pollution, there are all sorts of political issues, there's just a lot more than just thinking of the supplier and the consumer. There's an entire world out there. In an economic study, you would only look at these two welfare functions, but of course it's much more. Okay, and so our goal is to maximize this discounted social welfare. And again, if I do ignore this final term, and if I do look at this idealized model, then we can get a closed form expression for the optimal solution. Okay, so again, for the purpose of computation, just to give some qualitative insight, let's look at the simplest model, where everything is piecewise linear. So of course I've got, there's a price of power P of t, and times g of t. Now g of t can be negative, in which case it's the supplier having to pay back money, and that's actually how it works today. That if you promise power, you don't deliver it, then you have to actually pay a penalty, which is based on the real-time price. There's the consumer welfare, which is more complicated. It's the value of consumption times the minimum of my demand and what actually is available. And there's a cost of blackout. Whenever the reserves are negative, I'm going to have a penalty. And again, I have to pay this amount, P of t, G of t, to the supplier if G of t is positive. All right. So it turns out under these assumptions, you can write down the discounted welfare as just a function of the reserves. You have this V minus C times D, where little d is the mean of the Brownian motion. You might have a Brownian motion which is initialized at little d. And so this welfare function now is just a simple piecewise linear function of reserves. So and that's the thing, when you add these together, the P of t cancels out. It's irrelevant. It'll come back though. I just need it when I get to the market problem. Okay. So again, when you add together when you add together these two terms, the prices just disappear. Okay, so what's the solution? Well, I'll explain it. First, I'll give you, it's just a threshold policy. It makes the reserves constant, exactly constant. The amount of power you ask for minus the amount of reserves is constant. The target reserves is constant. I'll give you a plot in a moment. And the target is a constant times the log of the ratio of these value of consumption, cost of blackout, and C, the cost of projection of power. So it's very insensitive to these quantities under this diffusion model. But it's very sensitive to sigma squared volatility and ramp rate zeta. If you let the discount rate go to 0, that corresponds to average cost or average utility. And what this 1 over theta plus converges to is 1/2 sigma squared over zeta. So when the ramping rate gets small or the volatility gets large, this threshold gets huge. And what's the threshold? Well, the optimal reserves end up evolving as a reflected Brownian motion. So whenever you're below this threshold R bar, you're in panic mode. You say, everyone ramp up as quickly as possible. And then once you get to that target, you ramp down. But then you're below the threshold again, so you ramp up. So that's why there's chattering along this boundary. Okay. Yeah. Yeah. Okay. So 0 is where you actually pay. So if the reserves go below 0, that's when there's a cost of blackout. So well before that, you're in panic mode, and you ramp up as fast as you can. And so you end up chatting along this boundary here. And that's the optimal solution in this idealized model. Now, if I do change anything at all, then I can't give you a closed form expression, but I can work things out numerically, and it turns out you get very consistent results. And it's really, the central limit theorem kicks in very quickly is what it is. You're adding, you're basically adding up a lot of increments of something with low memory. You end up getting something that looks sort of Gaussian. And we've looked at lots of numerical experiments, and it's very consistent. Okay, so that's the case of what happens when you have no transmission constraints and you just look at the aggregate model.
So the fact that you don't cross the line, is that because you don't have a negative ramp constraint?
That's right. So if you had a lower ramp constraint, then what you'd end up with is you'd end up with a two-sided process. That's right. Up here you'd ramp down, and down here you'd ramp up. And I wouldn't be able to compute things anymore. So this is just the simplest example where I can get my main message across. And but the ramp down constraint would be much faster than the ramp up constraint, and the threshold would be very, very similar. So it's okay. If you have, I can't really give you say much, but it's remarkable you can solve completely the problem with multiple sources of power. So I've got a coal generator that can ramp up very slowly, but it's cheap. I've got gas turbines that can ramp up quickly, but they're expensive. You can solve that problem explicitly for this diffusion model. And just saying the available power is the sum of the two generators minus demand. It turns out that the cheaper resource ramps up whenever RFT is below some threshold. The more expensive one ramps up when RFT is below another threshold. And you can prove that's exactly the optimum. You actually can solve the dynamic programming equations that come up. So what you end up with is, if you look at the ancillary generation, which has to be non-negative, and reserve that two-dimensional stochastic process, it evolves as like a two-dimensional reflected Brownian motion in a rectangle here. So you go up sort of diagonally, and you chatter. This going down here is ramping down ancillary service and ramping up primary service. So it's an exchange. And that's why the reserves here stay fairly constant during that time period. And then once ancillary service is ramped down, the gas turbines are turned off, then primary keeps on ramping up, and you get a one-dimensional reflected Brownian motion here. So it's what Rich Sowers at Illinois calls the lollipop process. It's you're in the stick of the lollipop here, and then you end up in the candy over there. And so that's actually the optimal policy in this case, if you have a diffusion, a Brownian demand. And it's remarkable when you actually do dynamic program experiments with a discrete model. So actually, if you compute the optimal policy for a discrete time model with nothing Gaussian, just demand increments are 1 or -1 or 2 or -2. But you compare what you get from dynamic programming to what you get from the Brownian motion prediction, they're almost identical. I mean, it's, when you get to higher volatility, you see a bigger gap for the discrete models prediction, optimal threshold compared to the Brownian motion. But it's so similar that it doesn't even matter. So I'd love to understand better why it's so close, but yeah. Yeah. Mm-hmm. Well, if we have looked at the case where instead of being an independent increment process, the increments have memory. So they're actually a Markov process with longer and longer memory. And we again saw consistency. We don't know how to even compute the optimal policy anymore, but we then could just numerically find out what would be the best affine policy, this form. And we did find that the central limit thin variance was a pretty good indicator of where the thresholds would be. If it's truly heavy-tailed, there's no central limit thin variance, and I think it's all hopeless. I just think it's that's my feeling. I just don't know what to do. Especially considering as sigma squared, the central limit thin variance goes to infinity, the threshold goes to infinity. So all hope is, you might as well give up. Yeah. Okay. And now, so any questions? I wish I had some homework problems for you. I don't know. Actually, Tony, yeah.
If energy could be stored,
yes.
then the formulation would change.
Yes.
Right? Here you have a power generation.
Yes. Absolutely.
Function.
If energy could be stored, then things would be very different. And then it would be as if I had another very flexible resource. So I could, well, first of all, when I had too much power, I'd be able to store it, and also, if I could then hopefully have a very responsive extraction process. Because that's the main thing. Do I have a resource with a high ramping rate? Can I store the energy in such a way that I can retrieve it quickly? A fast ramping rate is gold. It means low reserves.
Right at the very beginning, you were discussing how you can get a large volatility in the price loops.
Yeah.
Now, are you taking account of the elasticity of demand? It seems to me
No.
there's something missing in your model.
No,
So
absolutely.
Something happens irrelevant to how you set the price.
Absolutely. So here demand is inelastic, as it is today. And flexibility demand is a huge benefit, which I'll discuss in a bit. Absolutely. Yeah. Oh, yes.
I have a problem with this because, in my experience, the reserve is there not so much for the variability of the demand,
Yeah.
but because you can get big problems. Well, you get problems with big generators.
Yeah, I'm glad you asked this. So, okay, so that was actually going to be that was going to be my homework problem after this part. So the first, I keep saying volatility in demand. Of course, it's volatility in supply, and the volatility in supply that California ISO is most worried about is far from like a Brownian motion. It's step changes. It's maybe basically a whole generator going out. So these sorts of models still, as long as, if it's always one generator that's causing the problem, then this analysis is pretty flawed. But the main value here is what's going to happen when we get to wind generation, and the volatility in supply will look much more like the model here. If you've got, yeah. So it's in smaller markets, you do have volatility to worry about, which will be part of that hedging. But with the introduction of wind generation, volatility in supply is going to, be much more similar to what this model is predicting.
A little bit confused.
Yeah.
In your model, the volatility is the demand.
No, it's actually, I should have said, it's all aggregated together. The volatility is from all sources, just lumping them all together. And so this would take way too long to get into, but I can't resist. Think of this more of as an advertisement than anything. I meant to bring this up. When you do have say in this case, this is Texas. This is actually the 3-node model that Ben and Danny looked at yesterday. When you have, look at this sort of linear model for power extraction and power flows on a network. We have this, what was it again? We have the flows, f of t, the vector of flows on different transmission lines is a matrix times the net generation at each node. So that's, again, generation minus extraction. Once you put in transmission constraints, it just becomes completely intractable. We can still formulate a social planners problem. They'd be the sum of the cost of generation, as we had before, from a primary service from ancillary service. There'd be a cost of blackout. If the extraction minus demand is negative, then you don't have enough power, so you're in trouble. It's completely hopeless to do what I've done so far, to get any kind of qualitative insight. Of course, you can set this up in a computer, solve the dynamic programming equations and all that. But what about insight? We want to get some sort of insight. And so that's why I say I would like to just advertise this. I don't have time to really be able to go into details. But there are all sorts of ways you can look at sort of projected dynamics. So look at aggregate models. So here's just one example. Let's just look at the sum of the reserves, extraction minus demand at each node. So sum of 3 terms. And the sum of the ancillary service. This is the total ancillary service of the whole network. Okay? And so maybe that's many, many sources. And what you then do is you define this aggregate state. RAGA, which is just in a 2-dimensional process. It looks just like a 2-dimensional process we looked at before. So you remember I had plots of reserve and ancillary generation just a moment ago. So now I'm just looking at aggregate values. And then you can borrow a trick from the heavy traffic theory in stochastic networks. Anyone who was here in March, I'm sure there were lots of talks on heavy traffic theory. And one thing comes up is an effective cost. So what that means is, given this 2-dimensional state, what's the cheapest configuration of the entire network which is consistent with that configuration? Take into account transmission constraints, take into account all the constraints that are in the network. But at least it becomes a static optimization problem. And something that you can solve offline just once. So I want to minimize this static cost here, subject to all of these constraints. And the main thing is that I've got this power flow constraint, that the flow is constrained to whatever capital F, upper and lower bounds on a transmission line. Okay? So what the idea is this is that this is an optimistic point of view. I've got my aggregate state, and when I know what's the cheapest place I could be that's consistent, it gives me a target. I might not be at that cheapest point, but I'm trying to design control policies. So it tells me where to go, And so my policy consists of 2 things. Controlling the aggregate state, which is a stochastic control problem, and then this idea that I want to go to the cheapest state that's consistent with that 2-dimensional process. And so that's a component of heavy traffic theory for stochastic networks. And this would take a half an hour to explain in depth. But again, there's 2 components. A target state from this minimization, and then analysis of a 2-dimensional stochastic problem, which is dynamic. And in terms of the effective cost, it looks like this. These are level sets of that effective cost. And the reason that they look so strange is that there are transmission constraints that become active along the boundaries of this purple curve. And this purple region. And what this purple region is, it's a monotone region. It's a region in which it's advantageous to ramp all generation up at maximum rate in order to reduce cost. Okay. Out here, it's not monotone because of transmission constraints. Ramping up wouldn't help me at all because the transmission constraints would just make the power worthless. And what you can actually show is that for this 2-dimensional stochastic problem, I can't give you a closed form expression, but I can prove to you that what an optimal policy looks like is again a lollipop process, but the lollipops change shape. So instead of a square shape, it looks like an affine enlargement of the monotone region. That's a general theorem for these processes. So you get you guess the dynamics of the aggregate process go up at maximum rate, shatter down here, and then become one-dimensional. And that's it. And so in terms of what it really means, I'll just walk you through what would you do if you're in that state, or that state, or that state, or that state. Let's just think about that. So in this first case, if you're up here, it means that Dallas, this upper node, is experiencing blackout. That's what it means. So anywhere over here, somebody's having a blackout. You've got because there's zero there, negative reserves. But it turns out that even though there's Dallas is experiencing blackout, ancillary service is ramping down at maximum rate. You know? And that's all because of these transmission constraints. And that's very complex. So there's basically, because of transmission constraints, the ancillary generators have to ramp down and the primaries are ramping up until a transmission constraint is relieved. And so you can get a lot of insight from this, basically. Just look at this aggregate model, you can get a lot of intuition. And it's sort of a starting point, and then you get a more refined solution to the total stochastic control problem. And just briefly, down here in this monotone region, that's where it's advantageous to ramp up everybody at maximum rate. So these two, everyone was in blackout, or maybe just Dallas was in blackout, I don't remember. But in these two cases, ancillary generation, primary generation do ramp up at maximum rate, as you might expect. Okay. All right. So good. So in the next 20 minutes or so, I want to show how you apply these ideas and to analyze a real-time market, and under the most ideal situations, in the case of inflexible demand. And at the end of the lecture, I'll try to say something about flexible demand as well. Okay. So again, an ideal world. So I've got this forward market for electricity, I'm assuming all it exists. So 24 hours ago, decisions were made, generators were scheduled, and now I'm looking at the real-time market, and I'm trying to worry about that residual demand process and the residual generation. So the reason we do this, we have this forward market exactly to facilitate the scheduling of these units, to set these thresholds and these hedging in the day-ahead market. But so again, it's clear that we need maybe not a real-time market, but we need real-time control. We have to be able to see if there's a breakdown or a surge in demand and respond to it. And today, there's a market solution to try to do that. Right? We have auctions every 5 minutes in the real-time market to make sure that there is adequate response in the case if more power is needed. And so the real-time market is the focus here, just because the results are most interesting in a way. That's been my main focus. Okay, so again, in terms of market analysis, we go back exactly to this problem we looked at before. As was pointed out, when you sum the two welfare functions, the prices all cancel out. But that's only because of the fact that the generation that the supplier is willing to provide is equal to the generation that the consumer wants to ask for, and which is, of course, that's the same thing. G of t is G of t. But to put this in as a constraint is how you actually prove the first welfare theorem of economics, which I'll explain. Okay, so again, the welfare functions can be defined with any price function you want, because in this sum, P of t cancels out. Right. Okay, so I mentioned before that I'm going to assume this perfect competition, this absolute key assumption of equilibrium theory, that there are so many players that there's no way they can manipulate the price. So P of t is exogenous. No individual could possibly change the price. And so that's the price-taking assumption in economics. Okay. All right. So again, the price is irrelevant, say in this piecewise linear case. We don't need that, but if you have the welfare function has a P of t times gs, the consumer has minus P of t times gd. If gd equals gs, you add these together, these cancel out. And that's true no matter what kind of welfare function I had here. This could be an arbitrary utility function. Okay. So here's what you do. Let's look at a Lagrangian decomposition. So I'm going to put a process lambda of t times this difference and maximize this over all possible GS and GD. So it's a maximum over two variables. Okay? So a moment ago, there was only one variable, the generation. Okay? But I'm looking at Lagrangian decomposition, and now I'm optimizing over two variables, GS and GD. And now everything separates. That's the beautiful thing about these economic models. And it just becomes, it breaks into two parts.
GT is the generation. So
Yeah.
what is GS and GT?
Yeah, this is, okay. GS is the generation that the supplier is willing to provide, and GD is the generation that the consumer would like to get. Okay? So in the social planners problem, this is just, they're equal. It's the same thing. What I want to do is I want to move towards the economic problem where the consumer solves an optimization problem and the supplier solves an optimization problem. And equilibrium means the decisions agree. So I forgot to say that, so thank you. Yes, okay. And so to do that, I start with the social planners problem, and just through this Lagrangian decomposition, it turns into into the game between the consumer and the suppliers. So what happens is this: once you put in a Lagrange multiplier, as I said, so I relax the constraint through the Lagrangian relaxation, and now I'm still maximizing over GS and GD, but now no constraints on GS and GD except for the individual constraints that they have. And it just separates. It turns into a maximum over GS and a maximum over GD. It's two separate optimization problems. So if the social planners problem has a solution, which it does in the case of Brownian demand and piecewise, and convex cost and utility function. And if there's no duality gap, so there's a Lagrange multiplier for which there's no duality gap, then it turns out that the optimal price, the equilibrium price, is just this nominal price P of t plus that Lagrange multiplier. And that price leads then to an efficient equilibrium. It means that given that price, the consumer can optimize on their own, and the supplier can optimize on their own, and their optimal solutions will agree and will coincide with the optimal solution of the social planner. So there it is. There's, it's a little bit of economics 101. This is a proof of the first welfare theorem of economics, that we've got a price functional for which there's an efficient equilibrium. It's efficient because it coincides with the social planner's problem. And the question is, what does it look like? So under these assumptions, this ideal world where I've got nobody can influence the price, and basically a little caricature of reality. I've got ramp constraints and uncertain demand. What does an equilibrium look like? Well, take the same assumptions as before. I don't have to repeat this, but piecewise linear setting. So again, I've got a linear value of demand, a linear cost of generation, and this cost of blackout. We know the optimal solution for the social planners problem. It was that reflected Brownian motion solution, constant R bar star. But the price, it turns out, is either 0 or infinity. So the cost, this optimal price, the P star I mentioned before, is this a function of reserves? It's a function of the optimal reserves. So there's the R star of t that I worked out for you in the first part of my talk. That's a stochastic process that's adapted to the demand process. And when that equilibrium reserve process is negative, the price shoots up to the value of consumption plus the cost of blackout, which is $100,000. And when the reserves become positive, it hits 0 in this idealized model. So as it turns out, this P star of t here, which is PE of RE, it's the marginal value of power to the consumer. So instead of the equilibrium price being marginal cost, as it would be in a static analysis, it's marginal value. And it's all about Lagrange multipliers. I mean, if I go to the doctor and say, hey, I have a heart attack, and the hospital says, well, we've got a lot of people behind you in line. I mean, it's not market power. The price is just the marginal value. I'm making exact same assumptions that would be made in any equilibrium study. is exactly the same thing, improving the invisible hand results that we all know and either love or hate. It's not market power. Even though the price is going up to the value of a heart attack repair, it's not market power. The prices are crazy. Now, this is a real caricature because prices don't go to zero. That's because I've relaxed a lot of assumptions. If I put back in downward constraints, ramping constraints, if I put some constraints on the consumer, then we would get something much smoother. In particular, if we had quadratic cost and utility, we get a smooth function of reserves rather than something piecewise constant. It's just a caricature just to give the idea. And so prices, this is just a plot, I've got this reflected Brownian motion for reserves. Whenever the reserves go negative, the price shoots up to what's called a choke-up price. It's the maximum price the consumer would ever be willing to pay. And if you look around the world, you'll see the same sorts of behavior. So Illinois deregulated before California, and we realized it was crazy within a few months. Prices shot up to $8,000 a megawatt hour when they used to be 20. And I don't know who did, but somebody said, that's crazy, we need a price cap. So they put in a price cap of $5,000. And look what happened. The area of that curve is the same as the area of that curve, I believe. So price caps, and we said, forget it. And we paid for it. I mean, our bills tripled that year. This was California during the fun days of Enron, where this is spinning reserves. Spinning reserves. These are generators just doing nothing but spinning, being available to help out in a crisis. Prices going from 250 to zero.
If prices went up enormously, then one side of the market was doing extremely well out of this arrangement. Because the money went somewhere.
Yeah, well, I have an answer to that. Give me 1 second. Okay. This is Ontario, so even in communist Canada, they have a price cap of $2,000.
Watch out, there's some Canadians here.
And it used to be you could go to the Amsterdam Power Exchange any day of the week, and you could see prices shoot up to $300 and down to 30, up to 300, sometimes up to 800. They've cut that off. They won't let you see it anymore. It's too bad. But all over the world you can see this. And I already mentioned the beautiful dynamics of prices in Australia. So I'm not saying I have the complete answer, but I think this definitely is a big piece of the puzzle. And basically the ramp constraints mean Lagrange multipliers. The consumer's saying, I want power. The generator's saying, I'm doing the best I can. And when you have a ramp constraint, it's a Lagrange multiplier. Prices shoot up to marginal value instead of marginal cost. Now, one more caveat. And I'm saying that the marginal value of electricity might be $200,000 a megawatt hour, which is infinite, basically, a lot more than $10,000. But amazing fact is in the equilibrium, the expected price is precisely the marginal cost. So when I presented this talk for the first time at Stanford, I was asked, fantastic, it is nirvana. I mean, what could be better than that? You've got prices, marginal cost, everyone's happy. But are they? I mean, can you imagine my average price is marginal cost, but the variance is infinite almost. The variance is basically that value. So some years I'm going to bring in, as you say, I'm going to make a fortune, and other years I won't make anything. And it's just, the risk is, the volatility in the income to the suppliers is so great, they'll never stay in business. There's just no way they'd even enter the market. I mean, they would never want to build this infrastructure to be involved in such a volatile market, where sometimes they make a fortune, sometimes they make nothing.
It's just partly because they haven't actually designed their plant and transmission system to suit this sort of market. Otherwise, it would be a different set of hardware that would almost never be a constraint.
It's a question. No, but it's a question of the ramp constraints are. You could say, well, maybe someday we're going to. Well, first, I could say, let's put in a parallel line of generators, and their total ramp rate will be larger. The network is a dynamical system. You can't just kick it. So there are inherent ramp rates that you just can never get past. And so you're going to need these sort of firefighters around. It's inevitable to be able to respond and ramp up. And it does happen all the time, all over the world.
Transmission constraints that you built in you could get rid of in having a serious influence by building more transmission.
Yeah, well, the feeling is, I mean, it's possible, but the feeling is if we really tried to over-provision against all contingencies, that wouldn't be worth it either. It would be so expensive. I mean, to be honest, my gut feeling is the real-time market doesn't make sense. So I mean, one of the messages I want to make during the panel on Wednesday is that the real-time market is very much like a market for firefighters, and it's, you know, we tried that in the U.S. in the 19th century. We had a free market for firefighters, and it wasn't very successful. and it worked, you know, and we could debate that later. Okay, so I don't have time for this, but I want to give you a few plots to show you what this model would predict with wind integration. And so basically, let's just say that Enron decided, out of the goodness of their hearts, to donate wind farms to every county in the UK. And so now you have 20% free energy from wind. What would happen then in a market setting, where you still would have to deal with, you still have coal generators and gas turbines that would have to come in to rescue you in emergencies. And so again, this is too complex to go through. But what we've done in this recent work is that we've looked at a coupled day-ahead market and real-time market. So in the day-ahead market, we come up with decisions for insurance for the real-time market, basically ensuring that we've got a lot of capacity on hand, and then the real-time market goes on and there's this added volatility. I mean, so because of the fact I've shown you these plots of the volatility of wind, just that's been subtracted now from demand. So the new effective demand is highly, highly volatile. And so I'm going to skip for the details. I'm just going to jump past those. You know, it's too complex, but just give you some numerics. So, someone asked about, is it the value of consumption, the cost of blackout? I think it is, but my graduate students disagreed. So they came with this very low value for the value of consumption. But we've redone the experiments where the value of consumption is equal to the cost of blackout. The results were identical. It just shifted. Take the real-time cost to be $30 a megawatt hour. The day-ahead cost to be a bit less. That could be coal generation versus gas turbine. And let's take the price in the day-ahead market to be something less than the cost of the real-time market, which is pretty much what you see today. Our discount factor, it was consistent with a 12-hour time window. And I just want to show you some numerics of what you get numerically from this. The ramp limit was 200 megawatts per minute. Our mean demand was 50,000 megawatts, and our standard deviation was 500. This was just eyeballing data that we've seen. Okay, and so what the two parameters we're looking at are, first, the coefficient of variation. The standard deviation of wind divided by the total. So like 2 gigawatts of wind in the northwest of the US. You know? So this might be only 0.05 or something. It could be a very small number. And then there's a percentage of wind penetration. So the total wind generation divided by the mean demand times 100. So those are the variables we looked at. And so first of all, of course, with greater volatility, a greater coefficient of variation here, of course the optimal reserve levels go up, because we saw the optimal reserves are a function of volatility. And with a higher coefficient of variation, higher volatility. And the K's here again are penetration. That's 20%, 15%, 10%, 5%, 0%. So that's the baseline. If you had no wind, you'd have these reserves. If you look at the total welfare, the solution to the social planners problem with these parameters, of course it crashes down with volatility. You know, it's costly. With this more volatility, you need more reserves, so you have to spend more money for generators just to be spinning, just to be there, the firefighters on hand. But you look at the consumer welfare, and it's amazing. So when you get to, and this is universal, we've looked at lots of experiments, when the coefficient of variation gets beyond 0.1, the consumer welfare gets so low they might as well forget the wind. They might as well just completely give the windmills back to Enron and just go back to the traditional system. And the suppliers just have a blast. They make a fortune. And that's even though they lost a big part of the market. So even though if you just do the arithmetic, they've lost 20% of the market because these communities are getting 20% of their energy free from wind. They're still making a fortune because they're playing the role as the fire department. You know, and this is just in this setting. Now, of course, there'll be price caps, right? I mean, they're not really going to be able to charge $100,000 a megawatt hour. But this is the unique efficient equilibrium. The unique equilibrium. There's no other equilibrium. So in this model, a price cap would mean the suppliers would leave the market, because then their average price would be less than their cost. They'd go out of business. There's no other equilibrium than this. So, you know, even though there's an idealized model, you know, it suggests some real, you know, warnings about how we're going to manage the new volatility with all the wind integration. Yep.
Could you say a little bit about the environmental
Oh,
welfare angle in this?
Yeah,
I mean,
yeah.
so- yeah.
Well, I'll get to that.
Okay.
Okay. In terms of environmental issues, that's really part of the research frontiers. I mean, so, you know, when I talk about efficiency here, I'm looking at this very myopic view of economics, where I'm just looking at some of the welfare functions of the consumer and the supplier, and the world is much bigger than that. So absolutely, I still see that as a frontier.
I was sort of wondering, you know, if you're ramping up and stuff more, there's more volatility, is it
in
less
that
efficient
sense.
in terms of
Oh,
production?
right. You know, I don't know. So maybe somebody here knows that. You know, in terms of the with greater wind, you know, I do have an answer. I mean, sorry, I misunderstood your question. That is another big issue. So I remember that plot. I can't go back to it. I had a plot of power in the northwest of the U.S. where wind generation went up to 2 gigawatts and then shot down to 0 in 1 hour. And so you've got to have a fast ramp rate of traditional power to make up for that, which means maybe more use of gas turbine power. And there could be environmental issues there as well as the cost. Absolutely. That's something we haven't thought about. But yeah, it's a good question.
Can you also comment on, sorry, I'm a bit unclear on it, but how the predictability of the wind might feed into this? So you can, the weather forecast there ahead.
Yeah, that's right. And that's what we're modeling here is the deviation between the forecast wind and the actual wind. If you go to the Irish Wind Association website any day of the week, you'll get something like this. You know, you get something that almost looks piecewise linear plus a beautiful Brownian motion, or maybe an Einstein-Uhlenbeck process. And I just can't imagine. I mean, I think that they do a beautiful job of this sort of the average, but getting rid of this, I can't imagine it's possible. But that's another research frontier. I don't know how much you could get sigma squared down. But these are our sigma squared is all what's that?
It does depend a lot on the geographical scale of the area you're talking about.
Right.
So
But
small geographical power systems like Ireland have it as bad as you can get.
Yeah. But the correlation between Ireland and the UK is very high actually, and in the US it's the upper northwest where we see there's a lot of diversity there, and it's still going from 0 to 2 gigawatts. So the diversity would have to go across continents, I think, to really bring this down. You know, to a. Yeah. Yes.
This event in the Northwest in BPA, 2 gigawatts in 1 hour.
No, that was I just picked. That's April. I think that's April 22nd. I was getting ready for this presentation, and I just went on one day. It was there. Any day of the week, go up there.
2 gigawatt change in 1 hour.
To make 1 or 2, yeah.
BPA.
Oh, yeah, absolutely.
Okay, I'll send them an email message and just find out.
But that's from their website, and it was a random pick. I didn't.
Yeah, that's a colossal change in 1 hour.
Yeah.
Is this in the Columbia River Gorge, I presume?
No, it's what's there. It's the whole area.
Yeah.
Yeah. It's their website. You know, the Bonneville.
Yeah.
Yeah. It's it might have been a few weeks and I picked through it, but I didn't even know about them until April. So it's just So in terms of questions, I mean, what is building bridges? I mean, anyone going to Ben and Dan's talk and in mine would think we were talking about totally different creatures, you know. And I mean, I've just made some very idealized assumptions to try to get an understanding of what would things look like in the best situation. And they've been looking at a competitive framework in different contexts, you know, looking at more long-term issues. And it would be really nice to build some bridges here. And I'd love to understand how to incorporate dynamics and uncertainty in a strategic setting. I mean, not this idealized setting that I've been looking at. And I couldn't resist this wonderful quote of David McKee. How could two smart people come to such different conclusions? I'm not referring to Ben and Dan. I'm referring to us. But I mean, you can go and Google wind energy, and you'll get such violent responses on both sides on the importance of wind energy and how we have to do it tomorrow, and how it's absurd. And you can just read any opinion you want, you know. And the same with markets. You could, you know, many people feel that price caps are a mistake. We should have no price caps in the real-time market. And many people think that we should regulate completely. And we just don't. I don't feel we have enough of a science to be able to answer these questions. It's just it's a lot of bridge building to build. Now, my belief is that we need to put more constraints on behavior, and then we'll have an analyzable system. Our highways are complex, but we put constraints on behavior. We don't tell people where to drive. We have limits on their speed. We have lanes and all that. It leads to incredible inefficiencies. Having 3 lanes go in Los Angeles, 3 lanes going in and 3 lanes going out, means in the morning you've got 3 empty lanes. It's inefficient, but it becomes a more reliable, predictable system. So once you put enough constraints on behavior, you get a system that's predictable. And given the importance of reliability and power, I think we need to think about that more. How can we better come up with trade-offs between reliability and efficiency when reliability is so important? And that's just not been debated enough, in part because the U.S., it would be absolutely blasphemous to even make that statement until 2 years ago. You could not put that in a proposal. And it's very exciting that now you can. So once you do this, once you do have a constrained market, then you know the players are going to have to figure out how to extract as much money out of it. And then there's lots of fun for us, sort of like Steve Shreve going to Wall Street to make money, explaining to Wall Street how to design auctions. We'll be able to go down to power companies and tell them how to extract money, say through our favorite Q-learning algorithm or what other statistical tools you'll have. And I really do think there'll be exciting ways of trying to build methods for setting up, say, maybe bid functions or whatever. So there's in terms of controlling supply and demand, there are 2 aspects. There's the demand management, basically flexible demand that will be talked about a lot this week, and also supply management, little simple things like controlling the pitch and wind turbines. Okay? Now, that sounds pretty trivial, but remember, it's a dynamical system. And that's the main message here. It's not just adding up the bulk amount of power in this scenario or that, there are all sorts of volatility issues as well. As I pointed out with wind, even though wind is free, its volatility makes its value much less. And so when we talk about, for example, demand response, we now have a coupled system of generators ramping up and down and suppliers ramping down and up. There's delayed information possibly, dynamics, and we need to analyze that huge dynamical system and not just do the arithmetic of how much demand response is there. It's not just missing money. That's a term you'll hear very often. But price caps mean missing money, as I pointed out in my lecture. And that there's missing money because of the huge cost in setting up a generation plant. The issue of exposure to volatility, besides just the mean money, is something that's often not analyzed in enough depth. And of course today, you know, with all the new introduction of renewables, especially wind, the volatility is something we have to think about from the supply side and the demand side. Do we have a sustainable business, and how can we make it more sustainable? And again, how to create policies. This is a little too narrow here, but how to create policies to protect participants on both sides of the market, and create incentives for all sorts of things, for research and development on renewable energy, you know, on fusion, whatever. The market itself is going to do it, and we'd like to be able to have some reliable long-term policies that will somehow stay in place, and we can hope have the right desired outcomes. I think that deserves research as well. I think it's something that Ben Hobbs and Danny Ralph are actually interested as well. So this comes back to this question. I mean, I threw in that third welfare term in my social planners problem, because that's a term that's often neglected when we talk about efficiency. There are all sorts of issues, like emissions of public safety, that are ignored when we talk about efficiency of the market. And I hope that the ideas discussed here will be a building block for these studies. I think basically there's a lot I don't know and a lot to be done. But I thank you for your attention.
We can continue for multiple team for some questions.
We just checked it. It was 900 megawatts in 30 minutes. And the largest change in 1 hour was 1 gigawatt. That's of the 10th of May. And the reason I mention it is because there's an awful lot of urban legends about how fast wind changes.
No, but this is from their website. I mean, this is oh no, it's not April, it's January. Sorry. Yeah.
Sorry?
January, not April. So I'd never known about their website until January, and in January I just found this data. Yeah. And that's the scale here is 2 gigawatts. And
So this is an hour.
yeah, this is let's see. Well, it went from near 0 to 2 in a couple hours, I guess. Yeah.
Yeah.
A couple hours, maybe not 1 hour.
No, it's, I'm not trying to be awkward. I'm just trying to make the point that people quote these numbers, right? And I think you have to be very careful, because if you talk to a power system operator and say it's 2 gigawatts in 1 hour,
Yeah.
well, if it's actually 1 gigawatt in 30 minutes, you might think it's the same thing. It's not.
Yeah.
So it's a sort of, there's a lot of numbers going out there. I mean, I've heard very senior politicians state that the wind in Texas changed by 3 gigawatts in 30 minutes.
Oh wow.
That's not true.
Okay. Yeah.
Oh
yeah, sure, absolutely.
Sorry, there's no doubt about operating a power system with a 900 megawatt power system swing in 30 minutes. Nothing about it is not the best.
Yeah. No, definitely definitely wasn't my intent to give faulty numbers. But this is what I was trying to say, and this is scary. This is very scary. To be able to subtract that from demand. Now, the great thing in California is that there is a lot of flexible demand. They pump water into California now, and that can be very, very flexible. They can just basically pump water when there's lots of wind and not pump it when the wind goes away. So California is saved by the fact that they do have inherent flexibility. It's less so in the UK.
Sorry, the situation isn't quite as bad as you show on that graph, because it's a question of how much the wind is predictable and how much of it is deviation from the
right. In our model, it's the deviation, absolutely.
So that's actually the actual generation, the actual wind generation, which may have been predicting something closer to that.
Right. So I would still push back on that, because even if it was perfectly predictable, even if you absolutely can compute the wind exactly, the fact that you'd have to schedule generators on Sunday to give all the power, and on Saturday to give no power, means that the volatility presented to the suppliers would be so high. You wonder if it'd be a suitable business model. They'd have to be paid much more to be able to stay in business, given the volatility, uncertainty, and how much money they'll make in a year.
Well, they make a great deal of money when the wind is down, and they won't make any money when the wind is high.
Right, it's a volatility.
They'll keep doing pretty well, I think.
And that's a question. On average, you'd say, oh, they're doing well, but then there's the variance. So some years they'll make huge amounts of profit, and sometimes none. Is that a sustainable business model? The volatility is as important as the mean.
Well, the volatility of the wind is on a sort of daily basis, whereas the volatility of some hydropower is more annual. So actually the volatility of hydroelectric power in places like Brazil is much more of a serious problem for generating companies trying to stay in business. But if the wind changes on a daily basis, it's less of a problem, I would have thought.
It's less of a problem, but it's still a problem. I still see it's more difficult for the generators.
So in these models, Sean, that you have considered, you view the supplier as a single entity, right? I mean, it's not, for example, if you have a grid across Europe and each country has its own production and pricing and so on, and have you considered that all such?
Well, we're working on that. So we of course, you can't compute anything exactly. We can only get approximations for the social planners problem in a network setting, and I've done some work on. And in fact, that's why I forgot the advertisement. So that's developed in part through this book is these relaxation techniques for stochastic networks. So bringing coal from Newcastle. This is a Cambridge University Press. And then you go to the market setting, and actually the same Lagrangian decomposition seems to work, and you can get locational marginal prices that
That
for the real-time
analysis
market.
would shed some light in other issues of borrowing and defaulting that we have now with the euro, for example. I mean, if countries borrow energy and they have to repay, and they, well, what does it mean to get bankrupt?
I don't know. Yeah, the cost of blackout is pretty high.
Hey, just to note that on that graph, as we see typically, the ramping up of wind is far steeper than the ramping down. And as a result of that, Vestas in their new turbines actually advertise how quickly they can be curtailed and scaled down, because they see a big market value in exactly that, in scaling back.
I see. Yeah.
And also, I think the earlier question was about, is there a carbon clawback if we use fossil thermal to balance wind? And those calculations have been done, and we lose between 1% and 7% of the carbon savings from fossil thermal plants. So there is a carbon clawback, but it's relatively small.
Great.
Again, returning to the question of volatility and prices, I mean, the POIRI did a study of the British and Ireland market until 2030, I think. And they showed the prices of not only they drop to zero, they go negative, because wind gets subsidies only when they produce. That means if it's oversupplied wind, then the marginal price they will bid is negative value of the subsidies, so it goes negative. Now, regarding the question which was asked earlier about volatility and how it affects whether it's a sustainable business. Again, when they did simulation and they showed how the power station operate. Basically, at the moment, for example, in this country, combined cycle gas turbines run 24/7 because they're at the base load. With wind, they will operate up and down all the time, which means that the mode of operation will change, but they will still make money, but only at the times when they operate, they will charge very high prices, and then the prices again will drop to negative. So what I'm saying is that the business is sustainable, but as you said, it will be highly volatile, and the consumers will see prices going up and down in a quite dramatic manner.
But that's so you did. I absolutely have to go back to this then. You see, so if you look at this plot, so what you're saying is that they'll be able to charge these high prices when there's you have to bring the firemen in and they'll get paid high amounts of money, and you see it here. The social welfare goes way up because of the fact that they get to charge these high prices for because the communities are in panic mode. But in this model, an idealized model, the average price is the cost. So I still think it's a very, very risky business, which first of all means that they're justified in getting a higher welfare. They're justified in giving giving all the CEOs $1 million bonuses maybe. But they're going to go out of business possibly on a bad year. It's just, the incredible, given the margins in this model are very low for the supplier. It's like the airline industry. I mean, one bad event and they go out of business. A volatile business like this is really, really risky. The airline industry is nowhere near as risky as this. And just one volcano, and it's just completely shaken up the airline industry. You hear about a volcano every month. So I think that I don't know the answer. I just think that just looking at mean values, like I have here, this is just a mean value. Only tells part of the story. The volatility this requires more thought, I think.
Last question, then break for tea.
Huge amount of this volatility, Sean, comes from the fact that you can't store electricity, traditional way of thinking, and that you can't manage demand. And that's a traditional thinking in the industry. But it seems to me perhaps that quite modest progress in that area is going to have a huge impact on this question of volatility.
I mean, having flexible demand on pen and paper is like having an incredibly responsive ancillary service owned by the consumer. And that has fantastic impact. In this model, it has fantastic impact in terms of everyone's welfare. It's absolutely true. But I just mentioned it's still a research question about that huge dynamical system, and about this, how much delay in information can be tolerated, and there might be some uncertainty in how consumers do respond to price signals and so forth. So implementing demand response still presents a lot of questions.
I understand that in the US there are people making quite a lot of money aggregating and selling megabars. We don't really have that in the same commercial sense, but I've met some companies out there that seem to be doing this. And you know, splitting the savings 50-50 with the companies that are using the power that they work with.
Yeah, that's another question. Yeah, so I mean, would options solve this problem, for example? I mean, you know, in terms of business models, there are definitely questions there that I don't completely understand yet. But, it's a good point.
We'll break there. Let's thank Sean for his fascinating, very clear talk.
Thank you.